In this video, I'm going to give you a quick example of how the first derivative test works to find extrema and classify them as either a max or min. Now, at the end of the last video, I kind of explained to you that this is a two-step process doing the first derivative test. First is finding your critical numbers, and second is testing intervals, or some videos that you'll watch in these lessons, I'll call this the sine chart. Now, the function that we're going to be working with here, f of x equals x cubed minus 6x squared plus 5. We've already done this first step in a previous video. So if you go to our intro to extreme values and fast forward to the 19-minute, 20-second mark, we've already done this first step and we've already found our critical numbers, 0 and 4. All right, so I'm not going to do that again. It's a pretty straightforward process. One thing I do want to mention though is this is a pretty straightforward example. This polynomial, the functions that you'll be having in your homework, you'll have a wide range of functions. I can't possibly show you examples for all the types of functions you might see. But basically any type of function that we know how to differentiate, that type of function could show up in your homework. So it could be trig, it could be exponential, it could be log functions. But no matter what type of function you run into on your homework, you need to understand that the process is the same no matter what the function is. Okay, so here, just as much as the example itself, you need to focus on this process that I'm going through. All right, so the first step in the process, no matter what that function looks like, is to find your critical numbers. Right, so that means we're taking the derivative of the function, whatever that function is, and finding where that function is 0 or where that derivative is 0 or undefined. All right, get your critical numbers. All right, once you've found your critical numbers, any x values in the domain of the function where f prime is 0 or undefined, assuming that's done, which in this case it is, then you move on to the second step. In the second step, you're going to test intervals. And here we do, in the sine chart, the basic idea is that we're going to see what f prime tells us about the graph of f. Because we already know that if f prime is positive, then the function is increasing. If f prime is negative, then the function is decreasing. So we're going to see what's happening on each of these intervals. So if my critical numbers in this case are 0 and 4, this breaks my number line. You can think of this as kind of being your x-axis on a graph. It breaks this x-axis into 3 separate intervals. Everything to the left of 0 would be one of those intervals, so that'd be from negative infinity up to 0. And then everything between the two critical numbers would be another interval. So here, from 0 to 4 would be an interval that we're interested in. And then everything to the right of 4, so from 4 to infinity. So what we're going to do is we're going to see what's happening on each of those intervals. We know exactly what happens at those critical numbers. At those critical numbers, the derivative equals 0. In other words, the function itself will be flat at those critical numbers. All right, so we know that the function's flat at 0 and 4 because f prime was 0 at those two numbers. That's what made them critical numbers. But let's focus on what happens away from those critical numbers. All right, so how this will work is we'll just pick any number in the interval and see what f prime does there. Specifically, we'll see whether f prime is positive or negative. That's why we call this the sign of f prime. The sign meaning positive or negative. All right, so we're going to pick a test value. Pick a test value in each interval. And with this test value, we'll plug it into f prime and see whether we get a positive or a negative number. So we're going to check to see if f prime is positive or f prime is negative at that test value. whatever happens at that test value, the same thing happens over the entire interval. All right, so for example, this first interval from negative infinity to 0, pick any number inside that interval and see what happens when you plug it into f prime. All right, so if I can pick any number in this interval, it's probably smart to pick an easy number to work with. So something from negative infinity to 0, let's just pick -1. All right, so let's do f prime of -1. So remember, we're plugging -1 into f prime here, not f, but f prime, to see whether f prime is positive or negative. And if I plug -1 into f prime, you're getting 3 times -1 squared minus 12 times -1. And really, I don't care much about what number I get here. I just care about whether it's positive or negative. All right, so this would be 3 plus 12 is 15. So the fact that it's 15 doesn't matter. What matters is that I got a positive number. All right, so let's go back up to what this tells us about the graph of f of x. If the derivative is positive, then that means that the function, the original function, is increasing. So over this interval, our original function is increasing, or you can think of it as something that's going up as you move left to right. So then we do this again for each interval. I'll do the other two a little bit more quickly. From 0 to 4, let's just pick 1. Again, just pick some number that's easy to work with inside the interval. F prime of 1 would be 3 minus 12. All right, so I get -9. And again, the 9 doesn't matter. The fact that it's negative is what matters. This is a number less than 0. So that tells me that over this interval, my function is decreasing. Or if you like, you can say that the graph is going down as you move left to right. Do this one more time for this last interval. Here, let's pick 5, something from 4 to infinity. Let's just pick 5 for our test value. And if I plug 5 into this, then I believe that comes out to 15 again. Again, the 15 isn't what matters. What matters is that it's positive. And if the derivative is positive, what that tells you about the original function is that it's increasing on this interval. Or if you like, you can show that this graph, the function, will be going up as you move left to right. So we have a pretty good idea of what's happening with this function. It's increasing from negative infinity to 0, then it's flat at 0, it's decreasing from 0 to 4, it's flat at 4, and then it's increasing from 4 to infinity. So you can kind of picture in your mind what this looks like. If it's increasing, and then flat, and then decreasing, and then flat, and then increasing, then you get a rough idea of what the graph is going to look like. Now, one of the main goals with the first derivative test is classifying extrema. Now, we've learned in the previous video that whenever a function switches from increasing to decreasing, you have a max. Whenever a function switches from decreasing to increasing, you have a min. Okay, so we can see that in the sketch that I drew over here. It was increasing, it was flat, and then decreasing, so we had a max. It was decreasing, and then at 4 it switched to increasing, so we had a min. All right, so the question is, what is our max and what is our min? Okay, now that we know where they happen, let's figure out what they are. Okay, so if I wanted to figure out what my actual max is, then I need to, remember this is the graph of the function f of x, then I need to plug those critical numbers into my original function to figure out what that y value is. Remember, the max would be the highest y value in the area, the min will be the lowest y value in the area. And now in this case, neither of these would be absolute max or min, because we see that the graph just keeps going down forever, so there's not going to be an absolute min, and it keeps going up forever on the right, so there's not going to be an absolute max. But at this point, you could also kind of tell, if there were any, you could kind of tell whether we have any absolute extrema, but in this case we don't. So to find my max and min, I know that 0 gives me a max, f of 0 gives me a max. So now again, I'm talking about the function itself, not the derivative. F of 0 is 0 cubed minus 6 times 0 squared plus 5, which obviously gives me 5. And then for my min, I need to plug 4 into my function. If I plug 4 into my function, f of 4, f of 4, I'm doing 4 cubed minus 6 times 4 squared plus 5. And you can double check me on this, but that should come out to negative 27. All right, so f of 0, this point right here, is the point 0, 5. This point down here, the min, where it switched from decreasing to increasing, was the point 4, negative 27. All right, so 5 is my max, and negative 27 is a min. Let's look at a more detailed picture of this graph that we were kind of sketching on the previous page. So all I've done here is I copied over all of the work we've already done. First of all, we know where the derivative, because of that sign test, we know where the derivative is positive or negative. And what that translated to is it tells us where our function was increasing or decreasing. So we know that from negative infinity to 0, our function is increasing. We know that from 4 to infinity, our function is increasing. And we know that between 0 and 4, since the derivative is negative, the function is decreasing. So this should kind of look like something we've really been doing all semester. Really from first or second week of class, I've been talking about this idea of increasing or decreasing. And one of your first assignments in the class was to take information about increasing and decreasing and sketch a graph that satisfies those conditions. That's really all we're doing here. So this is nothing new. We're only doing this in the context of derivatives now. We also know that f at 0 and 4 are critical numbers. F prime was 0, so that means that at 0, my function has to be flat. And at 4, my function has to be flat. In other words, its tangent line has to be horizontal. And finally, at the end of the last slide, we found 2 specific points on our graph. Remember, f of 0 was a max, because that's where it switched from increasing to decreasing. And f of 4, negative 27, was a min, because that's where our graph switched from decreasing to increasing. All right, anytime f prime changes sign from positive to negative or from negative to positive, your function's changing directions. If your function changes directions, then it has a max or a min there. So now to get a better picture of this graph, let me start with my 2 specific points. I have this point 0, 5, and you'll notice that since I'm going all the way down to negative 27, I scaled my x-axis by 5s instead of 1s. So 0, 5 would be this point here. And then I also have a specific point for negative 27, so that would be roughly around here. All right, now we know that from negative infinity up to 0, my function is increasing, but then at 0, it has to flatten out. So what that has to look like is something like this, where it's increasing, but then as, if I can get my pen to work right, it's increasing, but then as you get closer to 0, the function starts to flatten out. And then it's perfectly flat at 0. It hits that point 0, 5. from between 0 and 4, the function switches to decreasing. So it starts out flat, and then it decreases down to that point 4, negative 27. All right, so we start out flat, but then decrease, but then we have to get flat again when we get to 4. And then from 4 on, it's increasing. So it starts out flat at 4, but then it's increasing as we go. So it's probably doing something like this. All right, so without plotting any additional points, I only knew 2 specific points. I knew my max, or my local max, here at 0, 5. I knew my local min at 4, negative 27. And really that's all I knew as far as specific points were concerned. The rest of this graph was just based on where I know that this function has to be increasing, decreasing, or flat. I could be even more precise if I wanted to. I could plot more points. Maybe I could do a little bit of algebra and find out exactly where the x-intercepts should be. But the main idea is that we can use our information from derivatives to figure out what a rough idea of what a function's graph should look like.